In the previous video, we developed the model for the four-station serial line to facilitate our capacity analysis. In the second video, what we'll do is look at adding capacity to the buffers and then how to use Simio reference properties to facilitate experimentation and comparison between different buffer configurations. So this is the model that we developed in the previous video, and the difference between this model and some of the ones that we had done previously has to do with the arrival mode on the source. So rather than have an arrival time specified for our source in this model, we specified the on event mode and we used the triggering event as the output of M1. So when a part leaves this output node on M1, that's the trigger for creating a new model entity or a new part entity from the source. And we developed the experiment and we used our traditional queuing performance metrics, the utilization, the number in system and time in system, and discussed the fact that we had very high utilization, and that high utilization was expected because due to our arrival mode, we always have parts available for M1. Similarly, because we have infinite capacity buffers between M1 and M2 and between M2 and M3 and M3 and M4, we also expect at steady state for there to always be parts available for M2. So in fact, this system will never actually reach steady state because the departure rate from M1 will be exactly 1 and the processing rate for M2 is also M1. So if we were to run this model long enough, we would see the error message that we have seen previously, that we have exceeded the maximum number of parts in the system. However, that's not really of concern at this point because our interest now is in looking at changing the buffer capacities. So again, let's take a look at the standard library server object, and as we mentioned before, it has built in an input buffer, a processing queue, and an output buffer. And in fact, we can explicitly set the capacities for these buffers using the buffer capacity property group, and you can see that we have input buffer and output buffer. So what I'm going to do first is go in and set the properties for M2, M3, M4. And I'm going to set the input buffer capacity to 0 and the output capacity buffer to 0. And so the first question now is, well, why are we not concerned with the buffer capacity for M1? Well, the answer is that the buffer to M1, the input buffer and the output buffer, don't really play any role for M1 because the source object creates new arrivals only when the previous arrival leaves the node. So the buffering at M1 will have no role in the model. So we set the properties on M2, M3, M4, and now when we run in interactive mode, we see that there are never any parts in the input buffers to M2, M3, and M4. In fact, we have a single part occasionally in the output buffer for M1, and this represents the fact that the part cannot leave the node, the output node, while there is another part on M2 because we use connectors to connect the stations, and so the part or the entity can't leave this buffer until it has capacity on the processing station because the input buffer capacity for M2 is set to 0. Note that if we had used paths rather than connectors to connect the stations, then the paths would play the role of an input buffer. So for example, if I go to the connector between M1 and M2 and I right click and use the convert to type, and I convert the type to path, and then I go to the path just for visibility's sake and change the allow passing property to false. So now I have a path rather than a connector, and when I run the model, we'll see that the path can play the role of the buffer. So entities can back up along the path, which in fact is the equivalent of having an input buffer. And so that's the reason for our model where we were explicitly interested in looking at buffer capacity, we chose to use connectors. So for this one, I'm going to go back and convert it to a connector. So now we have our model of interest back. And what I'd like to do is go and run the experiment. So we have our same experiment that we had before. And so I'm going to run the experiment. And what we're going to see, so what we see now that we have scenarios, replications completing, is that we have significantly lower machine utilizations. Where we had close to 100 before, we've got closer to 50% utilization now. The number in system is significantly reduced. Of course, the number in system, the maximum number in system now is limited at 4 because we have no input and output buffer, so we can at most have 4 parts in the system. And then the mean time in system again is significantly reduced, as you would expect, as we're limiting the number of entities, limiting the number of parts in the system. The price that we pay for limiting the number of parts in the system will be in throughput of parts that actually make it through the system. So recall from previous videos that where we use throughput as a measure, we defined the throughput of the system as the rate that parts finish, or the rate at which parts depart the system. And so we measured throughput by using the input node at sync 1, and we basically track the number of parts that entered this node and then divided that by the replication length. So I'm going to do the same thing here. I'm going to add my response and call it throughput. And the expression I'm going to use is going to be sync 1 input buffer number entered divided by, and now here's something that's a little bit different. Because we have a warm-up period, I need to have the run time now, which is the current time at the end of the replication, minus run warm-up period. The reason I need run warm-up period to subtract out is because as the warm-up period works by running the model starting at time 0, and then at time 100, because we have the warm-up period set to 100 hours. At time 100, we clear all of the statistics but maintain the system state. And so to calculate the throughput appropriately, we will start counting entities that depart the input buffer at time 100. And so dividing by run time now minus run.warmup, we end up with the 100 hour of replication length that we're actually calculating, computing the statistics over. So now when we run the model, we can see our throughput calculation, and again, as we expect, this throughput has been significantly lowered from the nominal value of somewhere around 60 that we saw when we had infinite capacity buffers. So naturally the question is, what happens when I increase the buffer size? That's what we're interested in experimenting in. We've seen two values so far, the case where we have 0 capacity buffers and the case where we have infinite capacity. So suppose we go in and select M2, M3, and 4, and instead of having 0 capacity buffers, we change those to 1. And so now when we run the model in interactive mode, we can see that we have the buffering that happens at all 3 of our stations. And so what the effect of the buffering will be is to increase the utilization of our station and increase the availability. So when there's an extremely long or short processing time on M1 or on M2, the buffer will buffer against that variability. And certainly when we go back to the experiment, we're comparing the throughput that we have with 0 capacity buffers with capacity 1 buffers, and we should see the throughput increase. And so it is in fact increased from around 30 parts per hour to about 37 parts per hour. So we have recovered part of that lost capacity at the expense of additional time in system, and again additional parts that exist in the system at steady, the number of parts in the system at steady state. So clearly what we'd like to do here is compare the performance metrics, in particular the throughput, for different values of input buffer size. So we've seen 0, now we've seen 1, and we've seen infinity, and what we'd like to do is explore that further. Now clearly what we could do is continue what we've done so far and just manually change the values for the buffer capacities and then run our experiment and observe and record the value of the throughput. But what we'd like to do instead is look at how we can use Simio reference properties to simplify the process of defining the buffer capacities and then using those properties to simplify experimentation. So going back to our model, what we're going to do is bring up the facility view, and I'm going to select M2, the object instance, and go to input buffer, and I'm going to right click on the property name. Note that it's not the property value but the property name itself. And on the context menu there's a set reference property option, and what I want to do is create a new reference property, and I'm going to call this buff2 for the buffer for station 2. And so we see the value that I had previously has been replaced by the reference property, and we have this green arrow signifying that this is in fact a reference property. So I'm going to do the same thing for M3. So again, I'll select M3, right click, choose set reference property from the context menu, and call this buff3. And finally in M4, I'm going to set the reference property to buff4. So now we have these property values set at M2, M3, and M4. And if we look at the model properties, so in other words, I'm going to right click on model in the navigation window, click on properties, and we scroll down and we now see something under the controls group called the controls group lists the reference properties that we have defined for our model. So I have buff2, buff3, buff4, which are all defined at the value 1. So now when I run, I have the buffer capacity specified by these reference properties. And so I can easily go in the model and say, well, let's make this one 2, for example. And now when I run, I'm going to have a buffer capacity of 2 at M3 and still 1 at M2 and M4. And so what the reference properties let me do is easily specify the value for, in this case, the input buffer size. So now that we have the controls defined, or we have our reference properties defined, I can go to the experiment and we see that we have a new section under the experiment called controls. So previously we had the scenario, the replications, and the responses, and because we've defined the controls reference properties, they're now available to us as settable values in our experiment. And so when I run, the experiment scenario will pick up the value specified for the controls. And we see this is the same value for throughput and utilization and so on that we were getting when we had manually set the buffer capacities. So what I'm going to do is I'm going to reduce the run length, and you'll see why here in just a second. Let's make this 125 hours and reduce our warm-up to 25 hours. Note that the way we specified our throughput, we still will compute it correctly because we use the run now and the run warm-up period, and so when we change those values, that will automatically be picked up. So what I'm going to do is now rename my scenario. I'm going to name this scenario as 0 and then set my buffer capacities to 0. Now I'm going to define a second scenario where I define my buffer capacities as 1. We'll go ahead and do an S2 and make our buffer capacities 2, and let's do one more. S3, where our buffer capacities are 3. So now I have 4 separate scenarios. Each one has a different configuration of buffer capacity. So I'm going to run my model, run my experiment, and you can see immediately that we're running all 4 scenarios simultaneously. And so as they run, it's going to take a little bit longer to run because we're running now, instead of 10 replications, we're actually running 40 total replications spread out over our 4 scenarios. And we can now make direct comparison of the throughput values or the time and system values to compare these different buffer configurations, as was our goal when we started the video. So now you can see that I've defined additional scenarios, and so we are now evaluating the buffer capacities from 0 to 10 where we have equal capacity buffers. And you can see the corresponding throughput, time and system number and system values. Now note when we go to the response results and look at the SMOR plots, and I want to look at the throughput plot, you can see that all of the scenarios are plotted side by side, which facilitates the direct comparison of different scenarios. So I can zoom in if I want to see the SMOR plot values in more detail, as we have seen before. So I can now easily make comparisons of the results across multiple scenarios. And so in this case, when we go back to the design, you can see that we started out with 0 capacity buffers at 30. We know the maximum is 60, and so we could define one more scenario here, and so I'll just make it 500 so we can see how close we can get to that nominal value of 60, which we saw when we had infinite capacity buffers. So we'll see when this runs. Now we're getting very close to 60. As we saw before, when we had infinite capacity, we have significantly more parts in the system and time in the system. But when we go to now the response results, we can see those values. Let me zoom out a bit, and you can see our 500 value here. So let's recap what we have just done. So we use Simio reference properties, and again the idea is that we're using a reference to a model property to specify the value for an object property. So what we did in our model was we defined model properties. So if I go select the model from the navigation window, go to the definitions tab and the properties, we can see the 3 properties that we created called buff1, buff2, buff3, and buff4. And so what we did is we defined these properties, and then in the object M2, M3, and M4 we used a reference to the corresponding property. And so by doing that, the reference properties show up as controls in our experiment, which allows us to compare different configurations of those control values. So you can see that the use of reference properties makes comparison of different alternatives much easier than had we ran them manually and then tabulated the results to facilitate the comparison. So we will see much more extensive use of reference properties as we continue with the labs.